Hello everyone! Welcome back to a new video. Today I'm going to explain universal motors. Universal motors are based on DC motors. We see right here a shunt DC motor. But we can control this motor with AC current. Let's see. We have a positive alternation here. And let's see what the current does. So the current flows. This is our total current and it splits into our rotor current and our magnetization current. And we see out of this formula, this one is positive, so our torque is positive. Our motor will start to turn. But now, let's follow the negative alternation. So, we are looking at this, our total current, our rotor current, and our magnetic current. And we see this one is negative, but because it's times each other, it's also positive. So we see this motor will work, but we won't use the shunt motor for this, and it's quite simple. If you look at this diagram, we see our currents and our voltage. But what's the problem? Our self-induction coefficient of our winding, our magnetization winding, this big one here, is way bigger than that of our rotor. So we know it's going to be shifted, our current is going to be shifted back more. Those two currents won't change at the same time, which causes that sometimes our torque is going to be negative, so it will slow our motor down. Let's look at this graph down here. We see right here both are negative, and we saw here that if both are negative, our torque is positive. But now green, our rotor current, is already positive. But our magnetization current is still negative, so torque is going to be negative. The rotor will work against its rotation. The following line is again positive, because both currents are positive, and we saw here that if they're both positive, torque is positive. And basically that continues for the rest of the way. So we're not going to use a shunt motor. But we can use a series motor because our magnetization current and our rotor current are only allowed to switch at the same time because they're in series. So we'll use a series motor. But we have to do some fine tuning. First, we're going to look at this formula. We know our total impedance is going to be the square root of our resistance value of our inductor to the power, and our AC resistance of our inductor to the power of 2. And we know this is the formula for the AC resistance of our inductor. But because we only had this on DC, and now we have this total, our inductor has to be smaller than the series one on AC, because otherwise the current would be limited too much. So we have to take a smaller inductor if we're going to use AC. Most universal motors have a little thing you can click in where you can select full winding or half winding. Now we choose, okay, our winding is smaller. And I will want to direct your attention to this. You can see I split my magnetization winding in two. And that's because of a very clear reason. It's AC. The collector brushes are moving, and your rotor is moving. So you have a lot of the current changes a lot. So you have a lot of high frequency currents, and that's really bad for our motor. For our voltage down the line for all the other users on the line. So we don't want that. We're gonna use some filtering to trap the current inside of the motor. So we split this coil into two parts because we know out of this formula, if the frequency is high, the resistance value of our inductor is high. So the normal current with small frequency can easily pass through to our rotor and cause rotation. But the high frequency, bad current, will be blocked and kept inside of our motor. But we also don't want them to stay there. So that's why we have this three-conductor filter. If we know out of this formula, if the frequency is a low, our value of our conductor is really high, our resistance value, so current won't flow there, normal current. But if the frequency is high, like our bad current, our high frequency bad current, current will flow there, and it has a direct path to Earth, and it can leave. So that's basically how our universal motor works. Thank you for watching everyone, and I'll see you in the next video.